Yeah, so thanks a lot to the organizers for giving me the opportunity to present some of our work in progress actually this time. And also thanks for being so accommodating and letting me present in the second week. I had some trouble last week with arriving on time because of weather in Europe. So I will talk about some work that was done predominantly by Zhanpeng Fu from Shanghai Jiao Tong University in collaboration with Hongzheng Zhao at the University of Beijing and Roderich Moessner, who was here last week. So as the title suggests, I will be talking about engineering hierarchical symmetries in non-equilibrium systems. And so here's a menu for today. So first I'll try to motivate emergent symmetries and why we care about symmetries in the first place in physics. Then I will introduce a protocol for engineering a hierarchy of symmetries in prethermal plateaus of non-equilibrium systems. And then we'll take a look at a couple of applications, in particular some non-abelian and abelian symmetry ladders, but also equilibrium and non-equilibrium order. Let's see how time goes. Okay, so let's get started. Now, why do we care about symmetries in physics in the first place? I'm sure that everyone can come up with their own reason, but if you think about it, one reason why symmetries gained importance in physics is because they help us to determine the invariance of physical laws. And so here's one prominent example. The fact that the speed of light is the same in all reference frames essentially gave rise to the theory of relativity. This is an example of having a symmetry that helps us basically understand physical laws better. So besides physical laws, symmetries also help us understand conservation laws, and there's also a relation to integrability. And also symmetries are, as we know in condensed matter physics, particularly useful when we define phases and their transitions. But we also care about symmetries because they help us build minimal models. For instance, if we know the symmetries of a given problem, then we can postulate them and we can ask ourselves the question, what is the minimum model that satisfies those? And this is one approach, for instance, that has been used in the standard model, but also in Landau-Ginzburg theory. And in particular, now what we want is we want to be able to simulate symmetries, and we also want to be able to study their symmetry breaking. And so the question is, how can we do this using non-equilibrium systems? So that's what I'll try to answer in this talk. Now, before we start, there's just one other question that you need to ask yourself. So when are symmetries in real-world many-body systems exact? And if you think about it, you'll be faced with the honest truth that it's basically almost never the case. So we'll pretty much always forced to deal with some approximate symmetries. But even then, these approximate symmetries can prove very useful because they help us determine the hierarchy of different phenomena that our system would display. Okay, so now I'd like to specialize a little bit and move away from equilibrium, and I'd like to discuss emergent symmetries away from equilibrium. And I'll first try to explain what I mean by non-equilibrium drives and exactly which situations I will consider in this talk. One of the simplest non-equilibrium drives that you could imagine are periodically driven systems. In this case, you have a Hamiltonian. The Hamiltonian is a periodic operator of time. As we know, in this case, Floquet's theorem applies, and if we're interested at looking at integer times which are integer multiples of the driving period, that is stroboscopically, then the dynamics is governed by the Floquet unitary, which itself is generated by a static operator, the so-called effective Hamiltonian, that I will denote here by Q. But you can also go a little bit further, and you can sort of relax the periodicity constraint. So you can consider quasi-periodic drives. So in that case, the Hamiltonian is a function of two frequencies, omega-1 and omega-2. And the important thing is that the ratio of the two frequencies is an irrational number. And so in this case, the dynamics of the system is slightly more complicated than the periodic one, but nevertheless, we still have an effective Hamiltonian, which in this case can be defined with the help of a frequency lattice. Another way you can break periodicity are random multipolar drives. So in that case, what you do is you consider two building blocks, U plus minus, given by two generators, H plus minus. And then what you can do is you can take the two generators and you can arrange them in a dipolar fashion. For instance, U plus times U minus, or you can go the other way around, U minus times U plus. And then what you do is you can concatenate them in a random sequence. And as you do so, then clearly the periodicity of the system is broken. Nevertheless, you can still approximate the dynamics of UA and UB to be generated by some effective Hamiltonian, in this case QA and QB. And these are called random multipolar drives because what you can also do is you can consider higher order multiples, for instance, a quadrupolar sequence, etc. So these are three different classes of non-equilibrium drives that the talk is going to be pertinent to. And one common feature among all of them is that they possess an effective Hamiltonian, as I mentioned here, which we can now expand in powers of a typical time scale. For instance, this typical time scale can be the period of the drive, or it can be related to one of those frequencies or to this elementary time step here, capital T, etc. So I can take the effective Hamiltonian Q and I can expand it in a power series of this time. And what these systems have in common is that if you take this period to be small, or in other words, you consider the high frequency regime, then the dynamics of local observables as a function of time would pass through a long-lived pre-thermal plateau. And during this plateau, the dynamics is essentially governed by an effective Hamiltonian, which you can compute and up to your desired order and truncate it. And the interesting thing now in relation to the symmetries is that these objects can actually exhibit certain symmetries. So these would be emergent symmetries, and I'd like to just give you a couple of examples that hopefully some of you will be familiar with. So the first example is now more than 10 years old. It is the so-called Floquet realization of Haldane's model. So I don't want to go into the details of this, but essentially what you have is you have a periodic drive which, to leading order in this expansion, preserves time reversal symmetry, but the higher order corrections break time reversal. And so via this time reversal breaking, one can engineer topological effects and turn insulators, etc. But there are other examples. For instance, you can consider a situation where the leading order Hamiltonian has a U1 symmetry, whereas the higher order terms break this U1 symmetry. And what you can show in this case is that you can have symmetry protected, quote unquote, prethermalization, or in other words, prethermalization without temperature. And so the prethermal plateau that you see here would then be essentially protected by the existence of this leading order symmetry. I want to say that there are also other situations in which periodic drives can give rise to emergent symmetries, and one of them I think we'll hear about by Ashmi. I don't know where she is, but somewhere here in the hall on Friday. So there are other ways how you can have like emergent symmetries. And of course, it's important to mention here time crystals because they also have effective symmetries. In this case, you could imagine a prethermal time crystal where the leading order Hamiltonian would have, for instance, a Z2 symmetry, whereas higher order terms could break this Z2 symmetry. Okay, so now that I've shown you these examples, then a natural question that you may ask at this stage is, can we engineer symmetry breaking terms like in this series here, in a controlled way? And that's actually the main question that I'll try to answer in my talk. And the reason why we want to do this, as I showed you, is because it actually allows us to study a number of phenomena, a number of interesting phenomena related to symmetries and their breaking in a non-equilibrium fashion. Okay, so let me try now to explain to you how we're going to do that. So the idea is that I'm going to provide a constructive sequence, a protocol that would allow us to engineer a series of symmetries. So once again, here's the objective. So I'm going to consider a ladder of symmetry groups. So there's a group Gn, and then there's a smaller group Gn-1, etc. And what I want is I want to construct a drive such that the leading order effective Hamiltonian Q0 obeys the symmetry Gn. The first order Q1 breaks Gn to a subgroup Gn-1, but it obeys Gn-1. Then Q2 would break Gn-1 to Gn-2, etc. And then the last order would break G1 essentially to G0. So that's what I want to do. And just an example is, for instance, these symmetry groups can be, SU2, which in itself contains a U1, which in itself might contain a Z2. And then, somewhere in the middle is the trivial group, which only consists of the identity element. So if you think of the matrix representation of this effective Hamiltonian in the eigenstates associated with the largest symmetry group, then you're going to have like an SU2 block, then you're going to have a number of U1 blocks, and then a Z2 block. And of course, because every subsequent order breaks the previous symmetry, then you have couplings that connect the different blocks, and the couplings importantly scale as the corresponding power at which the symmetry breaking term occurs in that series. And now, if you think about a prethermalization, what you expect in such a scenario is that if you look into observables that correspond to these symmetries, the so-called quote-unquote order parameters, then they themselves would exhibit a prethermal plateaus. And what we'll see in the second part of the talk is that the lifetime of these plateaus can actually be well controlled. So for instance, in this case, the SU2 symmetry is the one that gets broken first. Therefore, the SU2 plateau survives for the shortest amount of time. But even though the SU2 plateau dies, the U1 plateau might survive for longer. And so for the Z2 plateaus, and of course, everything is upper bounded by the lifetime of the energy plateau, which for sufficiently short-range interacting systems is known to be exponentially long. Now, the state during these plateaus in the presence of those symmetries is something like a generalized canonical ensemble. This is essentially, the same way that you can go from a canonical ensemble to the grand canonical ensemble, where you add the particle conservation. Then you could consider adding more of those, conservation laws in case you find this necessary. Okay, so now let me illustrate the basic idea behind how we're going to generate this protocol. So the basic idea pictorially is essentially a spin-echo process. And here's the equation. So what I will consider is 4 unitaries that are concatenated in this way with 2 generators Q and H. And then the drive is designed in such a way that the Q terms are echoed out. And what this means is that in the end, I'm only going to have an effective dynamics to leading order by only having like H terms. So again, this is just a pictorial cartoon that I took from Wikipedia about what happens to leading order. So in order to construct the protocol, we're going to be using 2 steps. Now, in step number 1, let us start with some generator H0 that obeys a symmetry group G0. Now let me take a second generator, H1, and then this H1 will have a larger symmetry group G1, and in particular, the previous group G0 is a subgroup of G1. Next, we're going to set the generator Q0 to be equal to H0, and we're going to consider the same sequence that I just showed you, the same echoing out sequence. And if you do so, then of course, this unitary can be represented as e to the I of a new generator. I'm going to label this Q1. The subindex 1 corresponds to the largest group in this case. So now the question is, what is Q1? And to get an idea of Q1, one can apply Baker-Campbell-Hausdorff. And then what you find in the end is this series. And the series is organized in powers of T, which is essentially the control parameter here. So now let's take a look at these terms. The leading order term is just H1, because, as I said, so Q0 is equal to out, so it's just H1, and H1 has a symmetry group G1, therefore H1 obeys G1. Now the leading order term is the commutator between H1 and H0, and the largest group of H1 and H0 is essentially G0, right? So the commutator between H1 and H0 will obey the symmetry group G0. And then higher order terms, you can convince yourself they contain only nested commutators of H0 and H1. Therefore, they also obey the symmetry group G0. Now, in the second step, I'm going to add one more generator, H2. And as you can suspect, then it will be associated with the symmetry group G2 that contains G1, etc. And so I'm going to consider the exactly same sequence as before, except instead of Q0, now I put Q1, and instead of H1, I put H2, and the rest is the same. And again, the question is, what is the expansion, the period expansion of Q2? So you apply Baker-Campbell-Hausdorff, it's literally the same thing as above, except now, in these nested commutators, you find Q1. And Q1 itself has an expansion in terms of the period, so then this is not like a proper expansion yet. What I need to do is I need to plug in Q1 and reorganize terms. And when I do this, then I find the expression below. So let's take a look at it once again. So the leading order term now is H2, which obeys the symmetry group G2 by construction. The first order correction has the commutator H2 and H1, and now the biggest symmetry group between H2 and H1 is G1. So it obeys now G1. And now if you look into the second order term, there are nested commutators between H1 and H2. They will obey the group G1, similarly like before, but there's also this nested commutator which has H2, H1, and H0. And this one has the largest, has a symmetry group essentially G0. So now you can see how I'm pushing, every time a symmetry group to the higher and higher order in the inverse frequency expansion. And what I'm not going to show you, just because it's not really easy to follow, is the induction step. But in principle, you can keep doing this process over and over again, and you can prove that every time you'll be pushing, the symmetry one order. Okay, so in a nutshell, what we have is an iterative construction here, and this iterative construction can be summarized in the following way here, pictorially. So on the x-axis, I have time where I'm going to be applying these gates, and on the y-axis, I have these symmetry groups. So I'm going to start with, this elementary sequence with H0, H1, minus H0 and H1, and the whole thing then would generate Q1, which has symmetry group G1. Then I can come up with a, alternative sequence that would generate negative Q1. I can combine it together because now it has the same structure, and combine it together to get like Q2, and so forth. You can imagine how this goes further. Now, for those of you who pay attention, you might have realized that the length of this sequence, that is to say, the number of gates that occur here for a given symmetry group N, scales exponentially with the number of unitaries. And this, of course, an exponential is a hard wall, so it's difficult to beat, and this, you might think, could create a problem when you realize these sequences, but it's actually not the case, because in a realistic situation, how many symmetry groups would you consider, right? Like in a realistic model, they're really not that many. But in case you worry about that, I just want to say that if you assume additional properties, additional structure in your generators, then you can even find shorter sequences than this exponential. For instance, here's a simple example where I take 3 groups, G2, G1, and G0, with the corresponding generators. And now if I impose the additional constraint that this commutator vanishes, then a sequence which only consists of 6 terms would obey actually the properties that I want. Again, that every order every higher order in the BCH will break one symmetry at a time. And this sequence has only 6 terms compared to the one above for 3 symmetry groups, which would have 10 terms. So there might be like even simplifications if further structure is assumed. Okay, now let me take you through a couple of applications, because so far, this was just some dry theory. So I want to start with a symmetry ladder which contains, so this is the SU2 to U1 to Z2 to the trivial group, and this symmetry ladder contains reductions between both abelian and non-abelian symmetries, both between continuous and discrete symmetries, etc. So let's see how this looks in practice. So once again, I can consider a system, and this system has like an SU2 symmetry to leading order, which gets broken to a U1 symmetry, which gets broken to a Z2 symmetry, which in the end gets broken altogether. So here is the protocol that does the job. Now, I don't expect you to penetrate through, like the complicated math. The reason why I'm showing it here is because I think everyone can basically sum up all the generators here in this complicated sequence. And if you do so, you'll figure out that only H3 would survive. And H3 is the isotropic Heisenberg model. Therefore, the leading order effective Hamiltonian has an SU2 symmetry. And if you want to detect this symmetry, then you would use an order parameter, which would be any component of the total spin vector. Now, if you go through the math, you can show that, of course, this is how these generators were chosen, that the leading order term would reduce the SU2 symmetry to a U1 symmetry. And it's the U1 that's generated by the rotations about the z-axis. So this is also the corresponding order parameter. And then if you continue further, you'll see that the U1 gets reduced to a Z2, and that's a Z2 that's generated by a non-local like string order parameter And then eventually, if you go to higher order terms, you'll find the trivial group, that is to say that they have no symmetry. So let's see whether we can see these dynamics now, these processes in the dynamics of the system. So I'm going to consider an initial state, which I'm going to give a finite magnetization to. And because I want to also look at multiple components of the total magnetization, I'm also going to tilt this state. So the initial state here is the red arrow. So it's essentially a product of these states on the lattice. And this state you can kind of see has a finite Z and Y magnetizations. And then what I will look at is I'll look at the normalized observables as a function of time. So what this means is that I take the initial state, I evolve my state with this sequence, and then I basically normalize the expectation value by the initial value. So what I'm showing you here on the plot are those order parameters as a function of time in stroboscopic units. And what you see are three curves. Now let us first take a look at the blue curve. That's the one that corresponds to the SU2 order parameter. So you can see that it survives for about 2.5 orders of magnitude. A number of cycles before the plateau essentially disappears. However, the corresponding U1 order parameter survives for about an order of magnitude longer. So as expected, it has a longer lifetime because its symmetry is preserved slightly better in the BCH sense. However, it still decays if you wait sufficiently long, as expected. At the same time, the next level, the Z2 order parameter, seems to survive for as long as we can carry out the numerical simulation in that system. But then, we have checked that in a slightly smaller model, where you only take like a sub ladder of that, then you could also see the Z2 symmetry decay, etc. So this is like a very simple example, once again, where you see both breaking of abelian symmetries and non-abelian symmetries, and also discrete and continuous symmetries. So it's fairly rich. You can also, as you can imagine, use this to study various kinds of order, for instance, order related to SU2 symmetries or order related to U1 symmetries. And that might be particularly interesting from an experimental perspective, because it would allow you to, in a single run, basically study various ordered states. And the question that you may wonder at this stage is, there are various plateaus here, but how long-lived are they? In particular, as I start varying the frequency or the period of the drive. And the rule of thumb is that, at least what we find numerically, and we can also show this, by the way, in a relatively straightforward way, is that they follow, so the lifetimes of these plateaus follow a Fermi's golden rule scaling. So for instance, the SU2 symmetry breaking occurs to order T, and therefore the corresponding rate scales roughly as T squared, whereas the U1 breaking occurs to order T squared, therefore the rate scales as T to the 4, and so forth. Okay, so now I showed you how to see like some conventional types of order, but of course we have a non-equilibrium system. And so another thing you could do is you could start thinking about whether you can play also with non-equilibrium order. And a specific example of non-equilibrium order are discrete time crystals that I think Christoph Sacher talked about last week. So in particular, what we did here is we considered two different types of prethermal DTCs. One where we have a Z4 DTC, so a DTC with a Z4 symmetry, and then the Z4 symmetry group would be broken to the Z2 subgroup, which, if you wait longer, essentially gets broken altogether. So here's again how that works in practice. Now, to realize a Z4 DTC, I actually need a 4-level system, so 4 states, and then the X operator that usually would generate a spin flip. In this case, basically moves me or shifts the population through these levels in a circular way. So these are essentially the building blocks, the Z and the X unitaries. And then out of them, you can essentially create a model for a Z4 DTC. And you can consider a second term H0 that would break the Z4 symmetry to a Z2 symmetry. So the sequence that we will consider now is very similar to what we had before, except at the end of the period, we're going to apply this shift operator. And so what this is going to do is it's going to shift the population essentially, as I said, between these states. Now, if you do the analysis here, the effective Hamiltonian by construction has to leading order Z4 symmetry, which gets broken to Z2 symmetry, that gets broken, as I said, to the trivial symmetry, and the order parameter are going to be the populations of those states. So let us consider an initial state, which is a product state in a lattice of 8 spins, where the population is initialized in state number 3. And what I want to do is I want to let this state now evolve under the unitary UF. So here's the population. Here are the populations of the 4 different states as a function of time. And one thing that and of course, these are the populations measured every 4 cycles, essentially. So once the action of this operator has become trivial. And therefore, you don't see like the characteristic switching. I'm going to show it to you in a second. Instead, what you see in the population of level number 3 is a long-lived plateau followed by another long-lived plateau. And then, again, we hit the limits of our simulation, but eventually you can see how it decays further to an infinite temperature state. Now, if you zoom in within this first plateau, what you find are typical 4-fold oscillations of the population, exactly as you would expect for a 4-DTC. And if you zoom in later in time, then these 4-fold oscillations get reduced to a 2-fold oscillations, as you expect for a state that will move from a Z4 order to a Z2 DTC order. The reason why the amplitude here decays is because essentially your state becomes mixed between this 1 + 3 manifold, and then this blob 1, 3 oscillates with 0, 2, and then back to 1, 3, etc. So it's a partially mixed state. Okay, now the last example that I want to show you are topological insulators. So again, we were thinking, okay, where else are symmetries interesting in condensed matter physics? And the answer is whenever you're dealing with topological effects. So in this case, what I'm interested in is breaking a symmetry in such a way that I can start with a topological insulator. So as some of you might know, a topological insulator, if you consider a system with open boundaries, is characterized by edge states. So this is how the spectrum of such an insulator looks like, and these are the edge modes. But then if you look at the occupation, the lattice occupation of these modes, then you see that they're localized at the boundary of the lattice. So I consider a 2D square lattice, that's the x and that's the y direction. And then this is the population, and you kind of see that the edge modes live on the lattice. And now, what people have figured out is that if you have a topological insulator which has both inversion, so spatial inversion, and time reversal symmetry, and you break now just the time reversal symmetry, but you keep the inversion symmetry, then in certain situations you can have a so-called higher order topological insulator. And in that case, what you have is not edge states, but corner states. So in analogy, these are states that live at a corner. And the reason why this is interesting for us is because, again, this system, the HOTI, has a smaller symmetry group, and in particular, a smaller group that's even a subgroup of a larger one. So now what I want to consider is a sequence which allows me to realize this. And here is a sequence that you can consider. Essentially, what you do is you take H2 to be the term that you want, and then you start adding terms that break, once again, one symmetry at a time. And if you're interested, like how these operations act on the Hamiltonian, then this is shown here in that box. It's important to notice that in order to see a high-order topological insulator, you actually need a system with 4 bands, and this is shown schematically here. So again, doing the analysis, you can convince yourself that if you just sum up basically all these generators, you'll find that the leading order term is H2. So that's a conventional topological insulator with both inversion and time reversal symmetry. Then the leading order term breaks the time reversal but preserves the inversion. And therefore, we basically switch between edge states to corner states. And then any higher order terms have no symmetry whatsoever. Okay, so now what I want to consider an experimentally interesting state where I place all my particles at the edge. So that would be not quite an eigenstate of H2, of Q naught, but at least it will be like close to it. And then we're going to let the dynamics go. So here's what happens if you look into the dynamics after 2 driving cycles, so relatively early in time. And indeed, you see that, you know, this is how the state was constructed. You have like an edge state. If you wait long enough, then this edge state starts decaying, but the population at the corners survives for longer time. And indeed, if you take a look at the density, so this is the occupation, the normalized occupation of the corner states as a function of time, that's these red curves, you kind of see that it survives at long times. And of course, this is a non-interacting system. So unlike the previous 2 examples here, we won't reach an infinite temperature state because the system wouldn't thermalize. But you could imagine adding interactions, and then you would have exactly the same behavior as before. Now, in the last few minutes, I just want to mention something that we're currently looking into. Now, all of this is preliminary, so don't take, you know, like the what's written here on that slide for the absolute truth. But in particular, you know, I want to come back to this ladder SU2 to U1 to Z2 to nothing, and I'm mostly now interested in the first part of it because this is where you break a continuous symmetry. And whenever you break a continuous symmetry, then we know that there exists a gapless excitation, the so-called Goldstone boson. And in the case, you know, of the Heisenberg model that I showed you before, the Goldstone bosons would be the magnons. But now there is a problem because we don't really have an exact symmetry, right? Remember, you know, in our sequence, the effective Hamiltonian Q also has high order terms, and the higher order terms would break that symmetry, albeit weakly. And so it turns out that if you break an approximate continuous symmetry, then what you get is a gapped or a so-called pseudo Goldstone, a wannabe Goldstone mode. If you actually are a high energy physicist, you might know that this actually exists in reality, and pions are particles that are such pseudo Goldstone modes. Now, what this means, of course, is that once this excitation is gapped, then it will have like a finite lifetime, exactly like these particles. And so the question is now, can we observe such modes in our ladder in time? And I'm going to be using now the same example that I showed you before. Now, in order to observe such an excitation, there's a few requirements, and maybe there are even more, but at least the ones that we know so far is that you want to make sure that the temperature of your prethermal plateau is sufficiently small so that you can see the properties of that particle, so in particular smaller than the gap at the pseudo-Goldstone mode. And then the second condition is that the initial state has a sufficient overlap with the wannabe Goldstone excitation, right? So if the symmetry was perfect, then the excitation would be the magnon. Now the magnon is not a perfect excitation; it has like a finite lifetime, so it's broader in some sense. And so, you want to make sure that this is also the case. So, the state that we started from actually, we believe, has like such properties. So if you look at the dynamics, this is now the total Y magnetization as a function of time. Then as the U1 plateau basically vanishes, it vanishes in the process of these oscillations. So these oscillations occur in the process of vanishing. One thing that we believe we could do is by looking at the period of these oscillations and checking how these oscillations scale and also how they decay in time, we should be able to relate them to the properties of the wannabe pseudo-Goldstone mode in this approximately broken SU2 symmetry. And so what we believe now, but this is still to be confirmed, is that there's going to be an intrinsic decay of the Goldstone due to the finite gap, and the finite gap is brought in by the symmetry breaking term, so it's going to scale linearly as the period of the drive. But then, of course, the U1 plateau itself is not infinitely long-lived. In our case, the U1 plateau will itself decay to a Z2 plateau after another time scale, and so there might even be like a competition of time scales here in this setup. Okay, so with that, I'd like to summarize. Now, I showed you that it's possible to use non-equilibrium drives to engineer ladders of hierarchical symmetries in the prethermal dynamics physical systems. In particular, I want to emphasize the generality of the concept. So it applies to both continuous and discrete symmetries. It applies to abelian and non-abelian symmetries. It also applies to topological systems, etc. It's relatively easy to implement in experiments. In particular, the mechanism is very similar to the one that people use in NMR, like for spin echo, but also like it's very similar, like dynamical decoupling. In some sense, what we do is a generalization of dynamical decoupling to higher order terms in the effective Hamiltonian. And one interesting feature of these dynamics is that it allows us to investigate both equilibrium and non-equilibrium order in a single time evolution run. We also saw that the corresponding lifetimes of these prethermal plateaus, so basically the lifetimes of those ordered states, can be controlled by changing the frequency or the period here of the drive. And it exhibits Fermi's golden rule scaling. As I mentioned, the construction is fairly general. So, if you go back to this little derivation that I started from, it applies to any species. So it doesn't matter if it's fermions, bosons, spins, whether they're interacting or non-interacting, etc. I showed you examples for quantum systems, but of course it also applies to classical systems. And it will be interesting to see whether there's also generalization to open systems in one sort or another. One thing I didn't mention explicitly, but I actually did before, to generate the data, is that the construction applies both to quasi-periodic and random multipolar drives. So it's not really limited to flow case systems. And indeed, the data that I showed you, the SU2 data, was done for a multipolar sequence. It actually helped us see the decay. Otherwise, these plateaus would be too long-lived for our computers to simulate them. And essentially what you want in order to apply such a scheme, the sufficient condition is the existence of an approximate effective Hamiltonian. For as long as you have that, you can always play these games. What I also want to mention is that even though this is a sequence of discrete step drives or kind of unitaries, or you can think of them as gates, there is a natural generalization to continuous drives because I've only used the BCH expansion, but we know how to generalize the BCH expansion to continuous drives. You just, plug in the time-ordered integrals, and then you get the Magnus expansion out of that, etc. And then there are other open directions too. Maybe we want to generalize this to some local symmetries, etc. And so with that, I'd like to thank you for the attention, and I'd be happy to take any questions.
A very naive question that when you break the symmetry during your evolution, can you also treat it like a phase transition to calculate exponents or something?
Okay, that's a good question, and I didn't emphasize this. Maybe I should have. So there are no phase transitions that happen because the symmetries are never exact. So there is no symmetry breaking that happens per se. So these are crossovers. But if you look at the state, these states are going to exhibit pretty much the same orders that a proper phase would. So I think one can still speak of ordered states, but there are no phase transitions along the way. You could have phase transitions if you could have like thermal phase transitions in the process of heating up your system. That could happen, but that's slightly separate.
Hello. Yeah, thanks for the nice talk. So you showed how to engineer a non-abelian symmetry to leading order, but do you think there's a way to push it to longer times, like SU2? Because, I tried for a long time, many years ago, but it just doesn't seem to be compatible with the time translational symmetry group of a flow K or quasi-periodic drive. So anyway, I'd love to hear your thoughts about how do you push it to longer. Maybe I'm just naively wrong.
So let me see if I answer your question directly. But in principle, if you look at the construction here, what you can always do is you could imagine that, let's say that we have like these H2, H1, and H0 generators like they are. But now, suppose now that H1 and H2 share the same SU2 symmetry, right? Like H2 has an SU2 because that's the largest symmetry. Now, let's say that H1 would also have SU2, right? Then in that case, this commutator would also obey the G2 symmetry, which is the SU2 symmetry group, right? And so the breaking would occur at order T squared. So by doing this, you should be able to push the lifetime.
Right, but it's your choice of each one that makes it...
Absolutely, yes.
So but I'm saying that just take a given Hamiltonian, and I want to symmetrize it, give it an SU2 symmetry for longer than just t squared times. Is there a way to do that? Because, you know, I can do it for Z2 symmetry, right? I can do it exponentially long. Just pi pulse it.
Maybe we should, yeah, maybe we should chat like offline, but I think you should be able to parametrically shift the symmetry breaking term. Now, whether this is going to give you like an exponential lifetime, maybe not, but it will definitely crank up the power in the Fermi's golden rule scaling at which the breaking would occur.
Okay, thanks. Let's talk. Yeah.
So when you're talking about the continuous drives, there will you also need like a frequency which is like exponentially large in like the number of steps in this like symmetry breaking ladder as well, or is the scaling different to before?
So again, the exponential, this slide here, so the exponential occurs in the general construction. If you assume additional structure, you know, you could do better than an exponential. I just don't know how to, you know, generalize this so that it works like for an arbitrary number of symmetries. Now, what I mentioned when I said, what I had in mind when I mentioned the continuous symmetry is that if you think of the Floquet-Magnus expansion, if you compare it to the BCH expansion, then the commutator structure of these expansions is the same, right? So the only thing that you do when you add the continuous drive compared to a step drive is the time-ordered integrals up front, so the prefactor. And so what can happen is that, of course, if you get unlucky, this prefactor might vanish, so you might actually mess up some things with your drive, like certain orders. But in general, if they don't vanish, you would basically have exactly the same symmetry structure, symmetry group structure.
Right. I guess my question was more about like the scaling of the prethermal lifetimes in the continuous case. Like, do they scale the same way?
They would scale the same way, exactly. So the scaling essentially comes from this hierarchy here. Yeah, from this hierarchy, right? So you assume that, you know, Q1 is a perturbation on top of Q naught, right? And then Q1 would essentially scale as T, and therefore the corresponding rate will be T squared. Then you can do the same thing with Q2. And there's actually a rigorous argument why this works. The only time where it may not work is if you consider situations like this Z2 case where the order parameter would be a non-local operator, right? Like then strictly speaking, Fermi's golden rule doesn't apply. But in all other cases, you can just apply Fermi's golden rule. I don't know if it would be possible to you know, stretch those scalings to fundamentally change them from a power law to an exponential. That's, I don't know. But from what we see so far, it's consistent numerically with the power law. So I also have no good reason to believe that an exponential should be there.
Yes, going to the one before last question, do you think there is a property that could be true to all orders in the Baker-Campbell-Hausdorff expansion, but not in the exact result?
To all orders, but not in the exact result.
Yeah.
Intuitively, I would say no, but I need to think more to see whether I can.
Because the series is asymptotic in any case.
The series is asymptotic, that's right. So the other way around, you know, if I have a property of both generators, then of course it's inherited for sure by the effective Hamiltonian, right? So if both generators H0 and H1 have a symmetry, then the exact one will have the symmetry and the approximate one will have the symmetry. But what you were asking is slightly different. So I need to think about
such things exist because, for example, tunneling is, you don't see it to any order in H bar, and
then
still,
it's instanton effect, yes.
So it's not inconceivable.
Right. Yeah, it's a good question. Yeah.
We will take other questions during the break. So we are running a bit late. So let's thank Marin again.
Maybe the answer to this question is this DTC symmetries. I think if you naively do the expansion over one period, then I don't think you will immediately see the DTC symmetry in some cases, but it's actually there if you do the expansion in a proper way.